Welcome back to another edition of Hacking Arcade ROMs. It's been a while since we did our last lesson. Um, and in today's lesson, we're going to do something that's important that I would have liked to do a long time ago, but um, had to show you some other things before we could get to this point. So in all the examples I've given you so far, the ROMs themselves I've chosen, the games that is, I've chosen in particular because they all had one thing in common. They don't have any self-test, or at least they don't check the actual game code to make sure it has not been altered. Most of the games in the last, since like the early 80s, will actually run a self-diagnostic. And one of the things they do is they test the ROM code themselves to make sure that the game has not been altered either accidentally by the chips, getting corrupted, or intentionally by bootleggers, modifying things and, changing the game code like credits and putting their own fake company name and whatever. So I did that specifically because we had to get to this lesson. We had to learn some other things before we could get to this point. But often you'll want to hack a game, and you'll know what changes you want to make, or you'll figure out that you want to make changes down the road, and the game won't run. They'll immediately fail when the game tries to boot up because the changes you make, the system actually self-detects that it's been modified. That's called the game performs a checksum against its own code. A checksum is just something to validate the integrity of data. So we have to now explain to you how to get past that. And there's two ways to get past that. So I'll have probably two lessons. The first lesson today is going to be the easy way, simply bypassing the checks. You have to locate where the checks occur and then bypass them. Once you've done that, that's what I usually would like to do first, because you'll often want to make changes and you don't want to have to, you want to be free to make changes until you have a final state. Once you have a final state, it actually might be nice, rather than to bypass the checks, to actually just re-encode the checksum values so that they reflect the new game code with your changes. That way, again, if you do put it, these games are old, these chips can get old. If for some reason your game gets corrupted, the chips go bad, at least to some degree, the system can detect it and warn you, hey, this isn't the valid game code. So you can actually, what we'll do is we'll bypass the game code, and I'll show you how to do that in this episode. And then later on, once you know what you made all the hacks to your ROMs that you want, I will show you how to actually encode, or at least figure out the encoding scheme that's used, and then re-encode the new code that you have such that the game actually performs its checksums and it tells if you actually changed it, if it's got corrupted. Anyway, so how are we going to do this? Well, the first thing we do is we have to determine where the game check code is. So the easy way to do that is to find some code and alter it. Find some code that we know is not actual game code that will actually cause the game itself to corrupt. So we'll change something like a string, a set of text in the game, like the credit string, where it literally says credits, or the name of the game, whatever. We'll change something that is actually not game code, that's just data, and the game should fail. And as it fails, we can actually, what's called instrument that. We can determine where it's failing and find the code that's actually doing the checking, find where the comparisons are happening, and then just overwrite them. Okay. So the game code I've chosen is Akari Warriors. That's actually the main ROM Akari. There's actually multiple versions. Some of the Akari code, like Akari A, which is a earlier version of Akari Warriors, doesn't actually do any checks. Well, actually, I think it does it, but it doesn't care if it fails. But in this example, we'll use Akari Warriors, and that's just literally the word IKARI is the ROM set. So, as always, I have the game code here, my ROMs directory. I've already unpacked it. Okay, CD to Akari, and the game code for Akari Warriors is this ROM right here, ROM 1 and 2. Actually, there's two of them. The one we're going to change is ROM 1. Okay. I mean, you could try ROM 2 too. Actually, I think the ROM 2 actually is like the sound code for this game. But we're going to open up ROM 1. Trust me on this. We're going to find a string, and we're just going to change it and see what happens. So let's bring up our hex workshop and alter ROM 1. Let me clear the screen first. So I'm going to go to my E drive here, to my ROMs, Kari, ROM 1, and I'm going to just open that with hex workshop. Okay. And let's get that all on one screen. And let's just look for a string that we know probably exists. I know the word credit is in here, so I'm going to just search for credit. But you could, there's a good chance the word credit or play or insert is going to be, insert coin is going to be in the ROM somewhere. So just find it. You can use that other tool that I showed you how to find strings in ASCII, in the locations of strings in ASCII from an earlier episode. But I'm just going to use hex workshop because I'm here. So let's go to find. Let's click check text string, and I already got the word credit here. Look at that. Click OK. Boom, there's credit. All right. So I'm just going to go over here and change this 4. I'm just going to add 1. It's going to be from 43 to 44, which is going to make it a D rather than a C. So I'm going to hit 44. Oop. That didn't do what I wanted. I'm hit Control Z. Okay. I want to make this. I want to overwrite this. Let's overwrite that. 43. There we go. So it's a D here rather than a C. Before for some reason, it inserted it rather than overrode it. So now we have rather than credit, we have dreaded. Save it. We'll go to our main directory. It's not working. Oh, I'm using Windows. I have to change the C drive first. There we go. Okay, and let's just run. We don't even have to put in debugging mode. Actually, we do. We'll do main 64 debug Kari. And you see already it's telling me wrong checksum, which we expect. And let's hit F5. Oops, wait, hold on a second. Forgot to, let's try that again. Forgot to show you my screen. It was running on my other monitor, which I'm not recording. So let's just bring it over here so you can see that it actually fails, the ROM checks. We'll start it up. F5. You can see here it's running. And boom, there it goes. ROM error. Okay, CPUA ROM error. It detected that the ROM was bad. Okay, which is what we wanted. Well, you're thinking, all right, great. We know it's detecting that the ROM's wrong. How do I find where that happened? Well, we know if it's checking the ROMs and doing a checksum, that means it has to read every value in that ROM, do some type of mathematical or logical operation on it, and compute some value. And if it's computing some value based on every byte in that ROM, it's got to be reading that byte, right? So from an earlier lesson, we learned how to see how to stop when a certain byte is read. It's with a watch point. So all we're going to do is determine the location that we changed and set a watch point. Okay. I forgot to write down what location we changed. That stinks. Well, let's just go back to Hex Workshop real quick and find out what byte changed. So we'll go back to Hex Workshop real quick. We'll open it up. And again, you could use that tool that I showed you from an earlier episode. But I put dreaded in here, right, rather than credit. So let's just find string, and we had C, we did D. There it is. Okay. It's at location. Let me do that again, just because I'm find dreaded. Okay. So here it is. It starts at location B So B90 would be this one. It's B94. So write down B94, and we just now have to figure out what actual offset in the game code that is. Okay. In this case, it's easy because it is literally B94. But remember how we find that out? Okay. We go to MAME, and we're going to do MAME 64 list XML Akari, and we'll just redirect that to a file. Let's call it akari.txt. And then we'll do write akari.txt. And we just have to figure out where that ROM 1 was mapped to. What was the base address it was mapped to? So we find out here ROM 1, size about 64K, and its offset is 0. So remember from earlier episodes when mapping the ROMs to the actual game code, we have to take the actual ROM's address as we see in a hex workshop, which was B94, and then add that to the offset. Anytime you add 0 to anything, it's the original number. So the offset is actually B94, so it's nothing tricky there. Okay. All right. So now let's start up MAME in debug mode. MAME 64.listen.xml. We want debug Akari. I'm really just great today. Not make, MAME 64. There we go. And I'll move my thing over here so you can see what's going on in the window. I'm going to minimize it so it's real small. So we can, because we're really more concerned about the debugger at this point, not so much the main window. Okay. All right. And we want to set a watch point on that. We want to set a read watch point, so it's WP set, then the address. And if you remember, if you forget how to use a command, you can do WP set, and I just do help. And it tells me, nope, let's try this. WP set minus help. Help WP set. There you go. Right? So WP or WP set or WP for short. Then the address you want, the number of bytes you want to read, and then whether you want to read watch point or write watch point or both. Okay? So we want WP set 0xB94. We want 1 byte, and we want whenever it reads that 1 byte. Watch point set. We're going to hit F5 to start. It's doing its thing, and boom, it stops. Stop that watch point, reading byte from B94. Okay? That tells you, it shows you the address. And remember, this isn't the address that usually it's not the address unless it's like an elder. Don't worry about it. You'll remember, actually, if you watch your old episodes, elder just keeps getting repeated. It's usually the address above it that actually triggered the read or write. In this case, it was a read. And the address above it here is 1185. And the code is add a, and the add or the value that exists in the register HL. Okay? Well, the register HL is OB94, which is correct, right? That's the address that we altered. So it's taking the value of address OB94, adding it to A. And if you notice, right above that was the instruction load AD. So right above it, it loads something, whatever D is, into A, adds the value of whatever is in the memory address pointed to by the register HL, and adds that to A, which was just loaded from D. And then at the next instruction, it's going to load D back into A. So this is all these 3 steps is really a counter. It's loading some value, some counter, pulling a byte of memory, adding it to that counter value, and then storing that counter value back into D. D is your long-term counter, if you will. So we're going to read it. We're going to load D into a register, read a memory address, add that back into the register A, because adds always work in A on the Z80. And then we're going to load that counter A back into the long-term storage D. Okay? Well, it's not really long-term. It's a register, so it's going to be short. But in this case, it's our long-term storage. It's a very short-term, long-term, if you will. Right? And you can see, again, HL has that memory address we're looking for. Okay? And then let's hit F11. And the next thing we're going to do is increment HL. HL is the counter. So once we hit that, we'll notice it goes up one because it's going through every memory address in that ROM bank and adding it up. Okay. Then it's going to do some things here. Load A into B. Why is it doing that? I don't know. We do, but don't worry about it too much right now. Or C, blah, blah, blah. And then it's going to say JP jump not 0 back to 1184, which is up here. See what it's doing here? It's simply looping through each memory address and adding that value into D and checking some other counter values. But eventually, what's going to happen is it's going to be done reading all the RAM, all the ROMs in that case, at least in that bank, and it's going to get to this point. We actually want to get to this point now. So, because if I keep hitting 11, it's going to do this. It's going to do quite a while. There's a lot of addresses in RAM, or I'm sorry, in ROM. So let's clear that watch point. Let's do a WP clear. And then let's actually break at this instruction, because this is when the loop is done. Once it hits 0, once some counter, which is the counters of actually how many addresses it's reading and adding into this checksum, that's what's happening actually over here with this DEC BC, LD, BA, or C. Okay. What's going to do here, eventually it's going to get hit here. Once it's hit 0, it's going to break out. It's done computing. And it's going to do something with D. You can see it's storing D. It's loading D into IX plus 0. Again, anytime you add 0 is 0, or is the original number. So it's going to load back into memory whatever number IX is. And we want to know that number because it's actually storing the computed value. And somewhere later, it's going to compare that stored, that computed checksum, with a checksum that's somewhere in ROM, physically hard-coded in the ROM. So let's break here. Let's do a BP set 0x118E, hit F5, and boom, it breaks. Okay, it goes through its loops until it's done looping. And here we are, LD IX plus 0 in parentheses D. Okay. So we know D right here is the value CF. Let's just keep note of that. It's the value CF. That's actually the checksum value that it's computed, CF. Okay? And it's going to load that into IX plus 0. Well, IX plus 0 is whatever IX is. It's FEC7. So let's remember that, FEC7. Okay? So it's going to write the value, that counted value, that checksum value D, which is CF, and load it into IX, effectively IX plus 0, which is FEC7. Okay, so let's unset our breakpoint, BP clear. And now I want to know next time it goes to read FC or FEC7. Okay, so let's do this. Because eventually it's going to have to come back and actually, once it's stored that value, it might do some more computation. Who knows what it's going to do? But at some point, it's storing that data. At some point, it's going to have to compare that data to what it knows is valid. So let's just, again, set a read watch point. Watch WP set, and we want, in this case, that value that we just determined. FEC7, 1, and read. Okay? And hit F5, and boom, it stops. And you see here, we're at 11A5, which is sub B. Okay? So it actually read the address again, one step above. Load A with the value that is in memory at the location, whatever I is, register is, plus 0. So whatever IY is, which is, oh, look at that, FEC7, it's going to load that value into A, right? And we know A was, what was it, CF? And sure enough, CF. And then the next instruction, so that was the one that actually broke us. That's the one where it caught that memory access. Now what is it doing? It's subbing B. Well, what's B? B over here is CE. Wait a minute. That's interesting. It's just one less than what we actually computed, right? CE and CF, they're just one away. Well, isn't that interesting? Because we just changed the value. Remember when we altered the ROM, we just added 1 to whatever value is. So our value, that's an A that we computed, is actually just one more than whatever B was. Whatever was actually stored, which makes sense. We altered it by 1. The checksum was off by 1. In this case, a checksum, you can probably guess what the checksum operation is. It's probably just simply adding all the numbers. And whatever the sum of all the numbers is the actual checksum. Although it's looping. It's starting over after every 255 because we only have 1 byte of storage. And that's actually common checksum. Most checksums that I've seen in old arcade ROMs are either additions of every byte of RAM or every byte of the ROM, or what's called an XOR of the current XOR value, or the current value XORed with every other byte, just repetitively. But anyway, so we see the sub B, and then the next literal instruction is jump if not 0 to 11B2. So it's taking two numbers, subtracting them. If they're the same, that is, if the checksum passed, the value should be 0. And it would just continue on. But if it noticed that the value is not 0, that means that the values are not the same, it's going to jump to the 11B2, which is probably the code that prints out, error. And it actually is the code that prints out error. So, wait, how can we fix that? Well, let's simply make sure it never, if this is the thing, if it says, hey, if there's an error, jump here, let's just make sure it never jumps there. So it always goes to the next instruction. So what are we going to do? At address 11A6, we have 3 bytes that are the jump NZ11B2 instruction. Let's just NOP those out. Remember, NOPs on a Z80 is 0. We'll just go into Hex Workshop and turn this C2B211 value to X or 000000, starting address 11A6. So let's do it and see how it works. Close down Hex Workshop, or not Hex Workshop, main. Pull up Hex Workshop, or let's go to our ROMs. Kari, right click, and Hex Workshop. There we go. And the address that I said that started at, what was that address? It was 11B2, I think. So we'll go to 0x11B2. Okay. That doesn't look right. It was C2. Oh, no, it was 11A6. I'm sorry. I don't know where I got 11B2 from. That's right. Here it is. C2B2 11. So let's just overwrite that. 0, 0, 0, 0, 0, 0. Save it. Close it down. Close it down. So let's go ahead and start it up. Name 64 debug Kari. And let's go ahead and set a breakpoint. Let's just make sure that our NOP actually became a NOP and not we didn't accidentally hit insert rather than overwrite in Hex Workshop and alter the code altogether. Let's make sure that our NOP is actually a NOP. By breaking on the code that we overwrote. So we overwrote code. Where was that code? Was it 11AC? BP set 0x11AC. Or was it A6? So let's set 0011A6, load it up, and there we go. So here we go. We see our load A from IX, which was our address, FEC7, sub B, and then rather than our jump, we have 3 NOPs, because we put 3 zeros, which are 3 NOPs. Let's make it full screen and continue on, and we should see that it passes our checksum test. So I'm going to hit F5. Boom, did it. Let's just do that again. I'm going to hit F3 again, just to make sure that works. Let's do a BP clear, and just try that again. Just make sure it worked. I know it did, but There it goes. So you see, it's there, and we have credit here rather than credit. All right, so that was lesson 1, which shows you how to simply just bypass the checks. In the next lesson, I will actually show you how to compute, once you're done with your changes, how to recompute a checksum and embed it. We've already learned most of the ROM checking. To do that, all we have to do is, actually we have to do a couple things, but we'll talk about that next episode.